Good morning, good afternoon, and good evening, everyone. So today we're going to be moving on to a new topic, which is Taylor series, or here in this case, Taylor notes. So we're going to be talking more on the Taylor stuff now. And so previously, what we talked about was double integrals and how we could apply that towards rectangles, towards general regions, as well as with the usage of polar coordinates. Okay, so in Taylor, so here we're going to talk about Taylor polynomials and Taylor series pretty much. So what in the world is this? Me, I don't know. I'm just gonna go through it, see what happens. So in many problems in science and engineering, actually let me share that because I think this one's better. Yeah, I'm gonna share this one. So in many problems in science and engineering, we have some function f of x, which is too complicated to answer the questions we'd like to ask. So in this chapter, we will use local information near a point, x equals b, to find a simpler function g of x and answer the questions using g instead of f. How useful the answers will be depends upon how closely the function approximates f. Function g approximates f, and so we also need to estimate or bound. And so the error in this approximation is that function f minus our approximation function g. So let me just state that in my own words. What in the world are we trying to say? Okay, so we can actually, so in many problems, or in general, not even science and engineering, but in many problems, we have some sort of function, right? We have some function that we don't know. Say this is let's do an xy plane here. Let's say we have some function where if we're given some x value, we have a corresponding y value, or f of x. So we use these functions to answer questions in different kinds of problems, right? Like let's say if this were a car traveling, say x was the distance or x was the time and y was the distance that it covered, right? And so we would answer that using mathematics. But the thing is, sometimes these functions are too complicated. And so if some functions are too complicated, we cannot answer the questions we'd like to ask. Like, let's say, what if we're given some sort of function like this? I don't even know. Like, how in the world can you read that? Right? So stuff like that. I mean, I have some in when I do data science. I do have some graphs where I find it really hard to pinpoint or to read what a function really looks like. And so in this chapter, we will use local information near a point x equals b. So here we're going to find a simpler function g of x. So here we say sometimes f is too complicated. So we have to find, or we find, so we find some function, a simpler function that we could use. Let's say g, where x is equal to b, right? Let's say this was x equals b. We're trying to find something that's related to b. No, no. Yeah, this could be like, let's say, the distance, right? If we want to contextualize this, or let's say this is the time. So after some time, after X seconds, this is the distance. This is how many meters the car has covered and stuff like that, right? Or even actually, let's make it a calculus question. Velocity. That's the speed or the velocity of the car at this particular point at B, right? And so we take the derivative, we do all of those yada, 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 and then we get that. Okay. But yeah, so sometimes we find f to be too complicated, so we find some simpler function g in order to answer these types of questions. And so from there, how useful the answers will be depends upon how close g approximates f. So how useful our answers will be to whatever problem we're trying to solve depends. It really depends on our function g, which is approximately f. So from there, we need to estimate its error, or an error approximation is how we would like to call it. And that's going to be f minus g. Right. So let's actually go into our first chapter here. And I think it wrote it that way, which is funny. Okay, we're going to do a tangent line error bound. So what's a tangent line error bound? Let's go to the thing here. So let's say we have some scenario. Ken is at work. His car is located at his home, 20 miles north. 15 minutes from now, in the absence of any other info, his best guess is that the car is still at home. And there's a question here, how accurate is this guess? So Ken's at work, his car is located at his home 20 miles north, and 15 minutes from now, we don't know anything about the car, we don't know anything. So most likely that car is still there at his house. And so how accurate is this guess? If Ken knows his son will drive the car, so if his son will drive his car no faster than 40 miles per hour in the city, how far away can the car be in 15 minutes? A moment's reflection should give you the estimate or bound that his son can drive the car no further than 10 miles or 1/4 of an hour at 40 miles per hour. Okay. In 15 minutes, yeah, because, yeah. Uh-huh. Yeah, because 40 miles is 60 minutes. And so if we divide that to 15 minutes, then this should be 10. Yeah, 60 divided by 4. Okay, and then so that the car will be within 10 miles of home or no more than 30 miles from Ken. And we can also see this by using the fundamental theorem of calculus. Suppose Ken's son is driving the car in a straight line headed north. And suppose x of t is the distance of the car from Ken at time t. Then we have x of t minus x of 0, which is this integral right here. Okay, so let me actually write this out and see what in the world we're looking at. So here we say that, so Ken, let's actually draw it out. So Ken's at work. So we're saying, so Ken is at his work. So that's where Ken is, or office. I don't even, I don't know why I wrote it like that. Office, right? That's the office. His car is located at his home 20 miles north. Wait, am I sharing the right screen? Okay. His home is located 20 miles north. So let's say home. And the distance between these two things is 20 miles, right? And then 15 minutes from now, in the absence of any other information, his best guess is that the car is still at home. And we're going to determine how accurate is this guess. But Ken knows his son will drive the car. So his son, or Ken's son will drive car at, or no faster than 40 miles per hour. No more than 40 miles per hour in the city. And so how far away can the car be in 15 minutes? So in 15 minutes, then this is really just an algebra thing. Or no, not even an algebra, it's just arithmetic. So we say 40 miles in 60 minutes. And so that means if it's in 15 minutes, we just divide it by 4, then this is 10 miles. So that's what I was trying to say a while back. So in 10 after 15 minutes, Ken's son will have covered a distance of 10 miles, depending on where he drove the car at. Okay. So no further than 10 miles. So that the car will be within 10 miles of home or no more than 30 miles from Ken. Yes, so if he drove, let's say if this was the home, and he drove about 10 miles, right? So let's say he drove about 10 miles here. Then all in all, this should be 30 miles. This is the car. That's funny. Something like that. Yeah. Anyway. Okay. And we can also see this by using the fundamental theorem of calculus, right? So he's headed north there. So that's another thing when problem solving. We want to make sure we can get the picture down. So suppose Ken's son is driving the car in a straight line, which is highly impossible, but in this case we're doing it in a straight line. I have a license and I don't drive in a straight line. Headed north. Yeah, so here he was headed north. So that's why it covered 30 miles from where Ken is. So this is where Ken is. This is where his son is. So it's headed north. And we also want our x of t, or suppose x of t, is the distance of the car we're going to say from Ken at time t. So at a certain time, that's the distance of the car. So here we're making an x-axis, but it's a vertical x-axis. I would have done like y of t, but it doesn't matter. No biggie. It's just a letter at the end of the day. Then we have this integral here. So that's the distance. And then this is when x is 0, that's basically the car exactly at the office. We're going to subtract those, and we can actually convert it into an integral, 0 to x prime u du. Now let's explain in a bit what this means. But basically, if we were to, yeah, this is just, we integrate, right? How we integrate this stuff. We put x of t minus x of naught, x of 0, x of naught, right? It's fundamental theorem of calculus. So here, we see that x prime of u is actually the velocity, right? Or the derivative. And then when we integrate, it goes back to its position function, right? At time u. And so here in this problem, right, we know that when we take the absolute value of this thing, its velocity should be less than or equal to 40. How do we know? We said it here. If Kenson will drive the car, it's going to be at most 40 miles per hour. For all of you, between 0 and t. So that, okay, here's where we go into it. We're saying the absolute value of the distance and the initial starting point when the car is literally at the office is actually just the absolute value of this integral. Which is less than or equal to the absolute value of this thing. Which again is less than, from 0 to t, 40. And if we can integrate that, that's 40t. Right? So let me just go back to what in the world just happened. If we say that my u is just a letter, right? It doesn't matter what it is. But here's the velocity at time u. And so we know that if we take the absolute value of this derivative, right, it should be less than or equal to 40 for all u between 0 and t. That's basically what it means. And there's just a mathematical way of writing it, right? If we take the absolute value of this integral, then we can take the absolute value of whatever is inside the integral. And then we say it's less than or equal to 40. Then we integrate that thing. Okay. So there are a couple of steps above that need justification, right? So we need to justify everything we just did. And so first we use this equality, right? We use this idea. So 0 to t, x prime of u du. And we set it to be less than or equal to this thing. We sort of need to justify that idea. We say that the integral itself without the absolute value is actually just the area below the curve of the derivative, right? And above the u-axis minus the area which is above the curve and below the u-axis. Whereas the right hand, actually, let me just, I'm reading it anyway, so might as well just go to the thing here. because I'm also trying to understand what's happening here. But we want to justify everything that we just did. And so this integral x prime of u is the area below the curve y equals x prime of u. And above the u-axis minus the area which is above the curve. What? And above represents the area which is below the curve and above the u-axis. Okay, minus the area which is above the curve and below the u-axis. You just said the same thing. Oh no, above the curve, below the u-axis. Oh, I see what it's saying. Yeah. Whereas the right hand side, so this thing, it's talking about the absolute value of the derivative is equal to the total area between the curve and the u-axis, and so the right hand side is at least as big as the left. Secondly, we replace the function x prime of u, or that thing with the absolute value, by the larger constant 40, right? We did replace that with this one. And the area under the curve y equals 40 is at least as big as the area under the curve y equals that absolute value, right? And this was a rather long-winded way to get the same bound, but it works in general if my f prime of t, the absolute value of that, is less than or equal to some m for all t between b and x, then we have this. So let's actually write that out. Because I'm also my brain's gonna explode if I don't write this out. So in general, I don't think we've gotten to the topic yet. We're still trying to derive this whole thing. We say that if we have some function, we take its derivative of t, so this is a velocity function. We get its absolute value. It's less than some bound m, so m's are bound. And this applies to all t between b and x. I don't know where b and x come from. We're probably going to see it. Then we have this sort of inequality here. F of x minus f of b. The absolute value of that is less than or equal to m x minus b. Right. So I guess another way to write this, if we were to relate it to the thing above, is this integral from b x between b and x. This thing here is actually just, let me take that absolute value there. It's just this thing. F of x minus f of b. If we apply that fundamental theorem of calculus. And then we say this thing is also equal to the absolute value of this thing, or less than or equal to, yeah. Okay, it's just another short way of applying an integral. And then apparently that's the formula there. Mx minus b. Okay, let's test our understanding by writing out the reasoning behind this inequality. So the idea is that if we have more information, we can get better and better approximations. Okay, so for example, let's do an example here. Suppose Ken's wife called and said that their son left home driving north at 30 miles per hour. So Ken's wife called and said their son left home driving north. So the son drove north at 30 miles per hour. So 30 mph. Then we might guess. So we can guess, right? Mathematically. After 15 minutes, well, he is 30 divided by 4, or 7.5 miles north of the home, right? Or the house, or whatever. And so from there, we use a tangent line approximation. I think now we're getting into the topic, finally. Yeah, tangent line error bound. So we use tangent line approximation. And we'll do it as follows. So that distance from where the car is from the home minus when the car is at the home is around, so when we take the derivative, when the car is at home, t minus 0, right? We could do that. Again, it's just a tangent line approximation. And recall that the equation of the line which is tangent to the graph of y equals f of x when x is equal to b okay. Okay, now this is a more general thing. Now I'm gonna skip this. So we recall equation of line, or a linear equation, right? Y equals mx plus b. And we're gonna say this line equation is tangent to some graph, y equals f of x. We're gonna go with 2D stuff here. When x reaches some b, well then this equation should pass through a point that's b and then f of b, right? And at b, it should have a derivative or slope of f prime of b. And so that's going to be the equation of that line would be something like y minus, or actually, I'll write it my way. I'm not used to seeing it in that notation. I'll write it this way. Y equals the slope at b, some value of x minus b, then we add our y. There we go. Okay, and we actually call this a tangent line approximation, right? Because we approximate some tangent line to that curve. Or we also call it the first Taylor polynomial. Particularly for f based at b, right? Okay, I'm gonna screenshot the graph. So the reason why I wasn't drawing it is because I want to take a screenshot of the graph because I know they have better drawing than I do. Okay, so here's the graph. Oh, nice. Dang. UW really makes this clean. Okay, so this is my curve, my plane curve, y equals f of x. And at some point in B, this thing here, this line, is this. This line here is that. That's the equation of that line. Okay, there we go. That's that line. We plug in some x, we got some y, right? Cool. Okay. And so we found that the tangent line was useful for approximating complicated functions, right? The graph of the linear function, so that was a linear function, is close to the graph of y equals f of x if my x is near b, right? So we say that this thing here we're saying it's close to y equals f of x. Let's put what do you call this? Quotation marks on close, because you have to mathematically define that. Or it's not mathematically defined. If x is near b, right? And so in other words, what am I saying here? I'm saying that my function, in this case, is this linear approximation or this tangent line approximation. But we have to include some error. Now, the question here is, how big is the error? Well, I'm just gonna share the graph because that one's the way they drew it was pretty good. So the question now is how big or how can we quantify how severe is that error? Well, it's this one right here. Say this was the tangent line. Shoot. This was the tangent line, right? I meant to do it in blue, but oh shoot. No, it doesn't. That's nice. So the tangent line, and then the error is here. Oh shoot. I can't really. Oh my. The error is here, right? If we were to do it at some x. But at b, it's the exact same value. At b, right? Now, the thing that I like about these approximation techniques is if you actually zoom in, it will look the same. See if I can do that. I tried to zoom in. Okay, I can't do that. That's really cool. Okay, let me actually go to Desmos and show what this means. If we go to Desmos, let me turn. Okay, let's say I have a curve y equals x squared. If we take its derivative, it should be y equals to x, right? And here we see that, oh, let's say we look at some x equals b. Let's say b is 2. So at 2, once we get extremely close. So this is the meaning of close, because we don't mathematically know. Here we see that as we're getting close, I don't like zooming. Oh shoot. No, I lost it. That's not good. Uh-oh. There we go. But the idea is as we're getting close, we're actually getting really, really. Look at that. Now it's sort of twisting. Oh, I think that's the maximum. Well, that's not good. I can't zoom in anymore. Okay. Anyways, if we get super, super close, ideally it should we won't even see what the real curve is anymore. I guess we still do see it here. Uh-huh. Let's do this one. Oh, let's do this. This one, this one. Let's try this. Or no, maybe it doesn't really work at the end of the day. Oh, goodness me. Oh, wait, no, it's not just the derivative. We need it to be at that particular point. What do I mean by that? If this was, yeah, this was the derivative. We have x minus something. Actually, no, scrap that. It was like this, right? Okay, I can't make it general. Anyway, you guys get the idea. The idea is that as we're getting close to some value, it should kind of submerge. Like here, if we keep getting close to 2, it's sort of looking like a straight line. And little by little, it's going to look like y equals 2x. I guess the Desmos doesn't really show it here, but that should be the idea. Okay, never mind. Guess that doesn't work. But yeah, if we sort of zoom in, it should work. Okay, let me. Yes, that's the. Oh, what did I do? That's the error. Let's go back to the thing. Am I sharing the right screen? Okay, I thought it wasn't. Okay, wait a minute. Okay, so getting back to where we were. So that's the error. So now we talk about the tangent line error bound. Okay, why did my thing get skinnier? I swear my handwriting. Oh, it's because I'm far from the. Oh, shoot. Okay, this is better. Now we talk about the error bound of that tangent line. So here, let's say if we had the double derivative, now I call it a double derivative. Just because it sounds better, the double derivative. If we get the second derivative, we're bounding it to some m. And this is for all t between, oops, what am I writing? Feels like I'm writing hieroglyphics. Between x and b. Then we should have this thing. Oh, shoot. I think I'm lagging. Okay, I just saw my screen lagging, so I had to turn on the charger. So the error, we're getting the absolute value of that error is f of, so okay, when we say error, what is error? Right? Conceptually, it's the distance. If we were to give some x point, it's the distance of the actual value from the tangent line value, right? It's that distance. I do a lot of these in my other course, scientific computing, where we try to fit a curve. And then once we get the error by getting the absolute value of it. I also did it in my, okay, I'm actually I'm gonna post, because I'm also taking, or during my free time, I'm reading this book called Intro to Statistical Learning. So I wanted to just point that out. I'm also making some, or I'm also looking up some curve fitting there. I also see some curve fitting there. Okay, so this is the tangent line approximation, or the first, what do they call it? First Taylor polynomial. First Taylor polynomial. So that thing, and we get the absolute value of that. Oh, now this is different. Should be less than or equal to m half, and then x minus b squared. So that's the formula. So in the previous example, if we know that Ken starts with a speed of 30 miles per hour, let's look at that. Did I put the example here? Oh yeah, I did. Driving north. Okay. So in the previous example, now we go back to that example. I swear they should put Barbie here because there's Ken and anyway. So if we know that Ken's son starts with a speed of 30 miles per hour, and okay, here's the new information that we didn't get before. Accelerates. I don't know how they got no more than 20 miles per hour. And of course, this is going to be squared. Hour squared, right? While driving away. I don't know how they got the info. Or it's just, they just put it there because they wanted to. Then at time t is location. Okay. Or his estimated location. His estimated location is the following. So we say that x of t, right? Because that's where his distance is from the home, is around or approximately the beginning distance plus probably a derivative here. Yeah. His starting speed plus some time. So it's a linear, this is a linear function. And we're saying it's estimated because we're not sure with how he goes, right? He might bump into something, or I don't know. He might decelerate. That's another thing. But again, this is some linear function. Honestly, this is just m t plus starting point. It's honestly the same as that typical algebra thing, right? It's a linear function. Okay. And so the error in this approximation, so the error is the following. You get the absolute value. Oops. I meant the the tangent line approximation. This should be less than or equal to the m divided by 2 So in this case, 20 divided by 2. And then we have x minus b squared. So what is x minus b squared? T minus 0 squared. T squared. Right? I hope I got that right. X and b. So it's t minus 0 squared. So that's just t squared. Cool. Okay. So that's the formula. And so in particular, after 15 minutes, well, this is the error. X of 1/4. Right, because I'm assuming t is in hours. So we plug it in by hour. 1/4. And then this is minus x of 0. What is this? So he started off x of 0. What was the distance? Oh, shoot. Where is the example? Driving north. Maybe it's here. Yeah, so it's 20 miles. He started off 20 miles. X of 0 is 20 miles. We add x prime of 0. What was the speed at that point? 30. And then t, what's the time? Well, we already had it, so it's 1/4. And there we have it, right? And then this is at most less than or equal to 20 divided by 2. I hope I'm not, yeah, 20 divided by 2. And then t is 1/4 squared, which is 5/8, right? I'm gonna cancel. 1, 5. Yeah. And then this should be, oh, actually, my bad. We don't do this yet. You have to make this 16-ish, right? Yeah, this is 16. And then, yeah, and then that's when we cancel. We divide everything by 4. So this is 4, this is 5. And so this is 4 times 2, it's 8. So 5/8 miles. Cool. Let me. I love that song. Keep hearing it every time I go outside for some reason. I also like K-pop Demon Hunters. That was so random. Anyway, okay. So that's how we approximate these things, right? In a mathematical sense, as well as when we contextualize it. I actually have a couple more here. Yeah, we have like, that's fine. 2 more pages. Okay. Another question we could ask. This is another question. Why did I put my MATLAB on? What the okay. The heck? How long will it take Ken's son to be 25 miles from Ken? I would just answer this with algebra, honestly. So here we want to replace the complicated and unknown function with the linear approximation to answer this question, right? Cool. So we wanna do this. Okay, so let's just replace it, right? So this is 25 absolute value of x of 0 plus x prime of 0t equals, so x of 0 is 20. This one is 30 t. How long will it take? Well, that's what we're trying to find. We want to find t. And we just plug it in. So we get 25 minus 20 is 5. 5 over 30, that's like 1 over 6. Or 10 minutes. Because this is in hours. So we want to 1 over 6 hours is 10 minutes. Approximately. Cool. Okay. So that was an easy question, right? Because it's just algebra. Now, a more difficult question that I think we really need to apply our error bounds is when can be sure his son is at least 25 miles. How can we be so sure? So now we're quantifying how certain something is likely to occur. How certain is this? Well, that's where we use our error bounds, right? From Ken. And so to answer this question, we will have to write our error bound in a different form, right? So you have negative 10t squared less than or equal to x of t minus, and then my thing here, 20 plus 30t, right? Less than or equal to 10t squared. Ooh. So here, what do we notice? There is no absolute value anymore. If we want to rewrite this in an original form, the original form would be, so this was negative, my m half x minus b squared less than or equal to my x of t minus, then this is where I plug this in, my x of 0 plus x prime of 0 at t, and then this is my positive now. Right? So that's the formula for this, which I find to be interesting. I don't know. Maybe it's just a tool for Taylor series. I'm not sure. Yeah. So that's the formula that I can see, right? I could be wrong. I don't know, but that's something I could see here. Okay. So that's what we did. And then if we add 20 plus 30t, we add that term to the left hand inequality, then we should obtain, so we should have something like 20 plus 30t minus 10t squared less than or equal to this. Because we added it, right? So here, let me just take a note. I don't know what, I don't know. So let's say we want to add this term. We're adding it to the left-hand inequality. No, shoot. What did I do? That's what we get. Because if we add it to here, that's going to be 0. We add it to here, that's this thing. Oh, so to guarantee. Oh, so that's what we're trying to find. So another way to write this, at least 25 miles. We want to say that the distance, at least, so greater than or equal to 25, in a mathematical way. And so we want to make sure, so to guarantee that 25 is less than or equal to this. It's just another way of writing this, right? I just reversed it, switched the signs. Well, here's what we're going to do. We want to say that 25 should be less than or equal to this thing. So it's a very mathy way of doing it. So 25 should be less than or equal to this thing. Okay. And if we solve this for t, so this should be, I'm not gonna I'm not gonna solve for t here. We just do quad formula and then that's it. So this is 3 minus square root 7 half hours or 11 minutes. And so it might take this long if he is decelerating, because we really assume that the absolute value of the acceleration was at most 20. Okay. And then there's there's a proof of the fundamental theorem of calculus here. I'm scared to write this proof because I feel like I'm not gonna get it, even though I write it. It's been a while since I've done proofs. Okay, let me just go do it. Let's just try, see if we can get it. So that's the idea. Mhm. Okay, we're gonna try it. Right, so that's the idea, right? We want to be absolutely sure, we want to be mathematically true that Ken's son is at least 25 miles after 11 minutes, right? So why? So here now we're gonna say, or we're gonna define, why is this thing true? What makes this true? Oh, I wrote caps here. That's funny. What makes this thing true? So here, suppose that our x is greater than b, our desired output, our desired input b, then by FTC, or fundamental theorem of calculus, we have f of x, whoops, minus f of b is equal to this thing, dt. Okay. Oh. Oh, shoot. Okay. So here we treat x as a constant, and then we set, oh, what is this? Oh, it's an integration by parts. Okay, so here we treat x as a constant. I'm not gonna write that mathematically anymore because I know it's not gonna make sense. If I write this mathematically, it's gonna look like this. But I know I don't want to do it, so we're not gonna do it. It's a number, so that's a number. Then we set u to be my function, and my v to be t minus x, and then we do by parts and integrate by parts. Then here we should be able to, hopefully we're not gonna do, no, we don't do proofs in this class. I don't like doing proofs if I'm gonna be completely honest. Now we have this thing. F of x minus f of b, and we integrate this thing. Oh, what? My bad. A minus x. We get, now I'm x and b. Oh, uv minus integral v. So v derivative of this thing du. So f double prime. And then dt. Right? Oh, let's actually write these extra stuff. So du is the derivative of this thing with a dt. Then my dv. Oh, what is this? Think. uv minus v du. It doesn't matter actually. Yeah. So this was uv minus v du is that whole thing. That's the idea. Okay, and then from here, now what? I don't like this. F prime of b. What? Oh, because if I plug in an x, it's just everything's just 0. And then why is this not negative though? Oh god. Oh, you plug it in t. Do I plug it in t? Really? Oh, that's funny. Because I got x minus b. I'm pretty sure, yeah, I plug it in t, so I get f prime of x, x minus x. So everything here is just 0. Minus, and then we get f prime of b. And then we get b minus x. Oh, and then what happened here was I multiplied this negative here. So now we get this positive thing. Oh, okay, I see what happened. Cool. Okay, I trust the process. Sometimes I'm just confused with how they write it. Anyway. And then this is bx. Oh, what the oh, shoot. Then you switched it. Oh, you took out the negative, or actually you put the negative inside here. And then you switch the rows. Now it's x minus c. Well, that makes it more convenient. Now this is a plus. Yeah. It's just algebra, manipulating the equation. Okay. And then we subtract. So here we subtract this thing. So here we subtract this. Oh, what was my original? Oh, f of x minus. If we subtract this to both sides, it's just a proof. Then we should have something like this. The absolute value. Oh, this is a long one. Okay, so my f of x, right? This thing minus, what am I looking at? My tangent line approximation, f of b plus f prime of b, x minus b, done, less than or equal to my integral bx absolute value of my double derivative, and then my x of x minus d dt, and then it's less than another integral here, right? So from this, we say this was m, oh, there's a way to write it actually, mx minus t squared dt, right? Because we get the integral of that. Oh, shoot, not the. And then this is just, well, m over 2 x minus b squared. Okay, now I want to see what's a usable formula. So here we use the same ideas as the inequalities and the fact that x minus t is greater than or equal to 0. And so the case when x is less than b is proved similarly. Oh, that's the bounds. I think, yeah, we just proved it. Why is this thing true? There. This thing, the error bound, is less than or equal to this thing. So that was some proving. And we can also prove the case where x is less than b. I'm not gonna do it. No, I won't do it. Okay. Oh. Okay, I thought it was like a proving thing, but basically we're just gonna use that formula, plug in the bounds, and then we're good. Okay, let's just do that. Okay, let's do an example. How many examples did we do? I think that was like, no, those were just the preliminary examples to get to this thing. But that's the formula, right? Let me, yeah. Okay, cool. Okay, let's just do it. We'll get the hang of it with enough practice. Let's go to an example. 1.1. Here we're being asked to find bound for error in approximating. So here we want to approximate a function. We're going to say f of x is an inverse tangent, or arctan, or tan to the -1. Here we're going to use the first Taylor polynomial, right? Which is basically a tangent line approximation. Let's write out a bound for that. Oh, specifically based at b equals 1 on interval I. Now the thing about math is we're naming everything. And when I say everything, I mean everything. From 0.9, I'm gonna write it like that. I don't want to write it as 0.9 all the way to 1.1. Well, first, how do we do that? So the first step is to use the formula, right? So we find the tangent line. That's the first thing. Approximation. So how do we do that? We say that, okay, our formula for doing that is y or f or y, it doesn't matter. X at 0 plus x prime at 0 t. That's the formula we want to use. Or no, shoot. I think I'm wrong. Where did I know I highlighted that thing. Oh, there we go. That's the formula. I know I did kind of write it the same way. I just forgot. So at some b value, right? So f prime of b, x minus b. There we go. So my y. So what's my slope actually? First of all, what's my slope? I have to take the derivative of the same, right? So let's actually do the calculation. So we have f of x. If we do an f prime of x here, what's the derivative of my inverse tan? That's something I have to Google. I don't remember doing that. What is the derivative of an inverse tangent? Oh, it's 1 over 1 plus x squared. Cool. It's actually this thing. And so that means my f prime of b is 1 over 1 plus 1 squared, which is a half, right? My b is 1. Also, what's my f of 1? F of b. I wrote b, but b is already 1. My f of 1 is tan inverse of 1, which I believe is, I don't know what that is. Tan, oh shoot. Oh no. Calculator. My tan inverse of 1. Well, it's not an exact number. Is it just 5/4 or something like that? Okay. Cool. Okay, so it's 5/4. And then, yeah, we just plug it in. So y equals a half x minus 1 plus 5/4. Check. Right, so that's the first thing. We want to write the tangent line approximation. Good. Okay, what's next? We want to calculate the second derivative. Why do we want to do that? Because we want to use the formula. That's why. So, oh, the idea is we want to. So the tangent line error bound. Where did I should really like try to. Oh, there we go. That's the formula. So this thing. So I'm trying to get this one, that thing. Those two. And we need a second derivative somewhere. Because we can actually, we can just do that. Or just do this. Doesn't really matter. Hmm. I will see. We'll see how this goes. Okay. Hmm. So and then we calculate the second derivative. So my f double prime at x, which is, oh shoot, I have to do this. Okay, I'm just gonna write it out. So it's minus 2x, and then this thing squared. And then we have some x for interval I. When we have an x of interval I, we basically get absolute value. which is just 2x. That's really all the differences to it. We want to get rid of all the things, the negative values, right? How do we know? Yeah, because we already, it's 0.9 to 1.1, and these are positive numbers, so that's why. Cool. Now let's compute the derivative. We can show that our f double prime is decreasing on the interval I, right? How is it decreasing? Yeah, how is that decreasing? 0.9 to 1.1. So that its maximum value on I is equal to its value at x equals 0.9. Okay, so we want to do this. So we basically just plug in 0.9, 0.9 squared, and then we get this thing. See if that's correct. I'm not super sure. It is 1.8. This is 3.2761. Yeah, it's around 0.5494-ish. So 5.5. Again, we're just approximating at the end of the day. So it doesn't really matter. Oh, and so that's my M, right? So that's where we want to use this thing. We want to get the absolute value. And here we want to use this. I'm trying to get the formulas needed. So we want to use that. Right? We also say that based on the textbook, this is, or not approximated, rounded. Both work. To 2 decimal places. So that's that. Let me see how long I am on time. Okay, I'm a bit low on time. Okay, so here, once we set that idea, and now we want to use the tangent line error bound. So here, we use this idea. So again, how do we bound this thing? Well, we have our inverse tangent. So that's this one minus this thing. So minus the tangent line approximation, which is, I think it was 5/4. Or what did I do? 5/4, yeah. Plus a half x minus 1. Oh, wait a minute. What the? X minus 5/4? Why 5/4? Wait, whoops. Did I mess up? What? What happened here? 5/4. Yeah, what the? Became 5/4 for some reason. If we use a simple function, so what? 1/2 x minus. Oh shoot, I'm lost. Don't know how this became 5/4. I was expecting a 1. Or yeah, I was expecting a 1 here. That's all the formula. X minus b. What do I feel like it's x minus f of x? What? Where did I get f of x actually? Where did I get that? F of 1. Yeah, it's an F of B thing. Okay, that's really weird. I kind of assumed it to be. uh, Apparently that's pi fourths. I'm gonna check up on that. I'm gonna check that later. Okay, this is less than or equal to 0.55 over 2. Of course, we got 0.55 here. We divide it by 2, and then x minus b. So x minus 1 squared. And this is less than or equal to... Also, how did it get 0. How I get that number? What in the world? Yeah, actually, I don't know how to solve for that. How did... because it doesn't really plug in anything. That's the thing. Or from this interval, maybe? It doesn't... Hmm. It's not from is it from the interval, maybe? I think it's just from the interval. Let's see. 0.9, let's subtract 1, square that thing. 0.01 times 0.55 divided by 2. Oh, that's where they got it from. So I plugged in the 0.9 here. What if I plug in the 1.1? Oh, I get the same thing, yeah. So around 0.0028. Yeah. Previously I got was 0.00275-ish. So yeah. And so that's the error bound. Now, what does that mean? If we use that simple function, I'm still confused. Where did it get the pi fourths here? It really doesn't make any sense. Pi fourths doesn't make any sense. What? Okay, I'm gonna check that later. Um, Tangent. Yeah, this is tangent minus f of b. So f of b is pi fourths. It's derivative f prime of b. Yeah, because I did get it here. That's the funny thing. Yeah. And then somehow this turned into a pi fourths. Or I don't know. This could just be like 1 or something. How close is pi fourths to 1? It's like really close to 0.785. I don't know. To be honest, I don't know what this is. It just popped out of nowhere. Okay, let's just go. Yeah, let's just. So that's the. Yeah. So if we make use of that simple function, the y equals pi fourths plus 1/2 x minus 1, instead of the more complicated tangent, inverse tangent, then we will have some error in the values of the function of no more than 0.008 when x is in the interval I. So this is really good when we're trying to approximate stuff in different kinds of functions, and we do an error bounds, and we can identify the error, and then it's really up to us on how we want that error to be, bigger or smaller. That's up to our discretion. Okay, this is, I believe, the last example for at least for this notes. And I'm gonna move on to the section 2 after. So 1.2. So let's use that same function, that inverse tangent function. Now I know why they're making us do this, because this one's a really complicated function. We want to find an interval j. So here now we're being asked to find an interval that will give us a specific error. That error is at most 0.001 on j. So how do we find that interval? Well, if we want to make it smaller, then it should be smaller than the interval I that we have, right? So a smaller sort of distance from each other. Since 0.001 is less than 0.0028. And so we're going to use that tangent bound error thing again. Tangent line. What is it? Use tangent line error bound. I still don't know why that's a pi-fourth. I'm going to be. Wait, did I mess something up? I feel like I. No, it's really x minus b. But b is 1. Ah, what's the reason behind it then? Okay, let me just ask GPT. I give up. Let me just do it like right now. I'll ask why. Uh, can I? Oh, I can't scroll down. Okay. Yeah, that here. I'm gonna show you guys what GPT is saying. Okay. I put the first step. Make sure I put these two. Oh, copy. Nice. You already have the tangent line. Oh, we did Lagrange. No, not that. Okay, those are the next steps. Looks good. Yeah, in the final step. Why was it x minus 5 first? Shouldn't it be x minus 1? Oh, so okay, so it was wrong. Yeah, I was like so confused for a bit. So apparently it's a typo. Okay, right. So I'm gonna change that then in my new Taylor notes. Now this should be 1. Because I really don't see it being pi fourths if we're following the formula. So here we're gonna use the tangent line. Oops. Can we just go through this example and then we're done for the day? So here we're trying to find some interval j. So again, we use this tangent line approximation, subtract it to the linear approximation, plus my derivative, so a half. I wrote this in a very weird way. Forgot to add the absolute value there. This should be less than or equal to 0.55 half. And so the error will be at most 0.001 if this thing is less than 0.001. And then from here on out, I just solve for x. So for x, I would get that type of value. Right? So what does that mean? Now, how do we find the interval from that? Point 0.0603, right? So what is this? What does this tell us? Well, this tells us that, yeah. Okay, now I find this a bit confusing. So what now? How do we find the j interval? Zero zero 36364. Okay. If we add the one, okay, it doesn't really like tell me how to do it though. What is this? Okay, let me just go back to GPT and ask it because uh, I feel like there's also something wrong with the notes itself. That's also my concern, right? Okay, let me just quickly ask. Okay, so we want it bounded. Okay. Around. Oh, so that was the final step. That's so annoying. That was actually really annoying. If we want a symmetric interval, so what we want to do to get that interval is basically we want to subtract one from that and then we add it to the other. And that's how we'll get that. That's so messed up. Okay. That was tricky. So we want to be able to, then here we add this thing, which is around like what? Like 0.94. And then the other one was, I'm just gonna put the exact numbers they did in the textbook. Then the error should be at most 0.001, right? That was annoying. Yeah, these are my x intervals. So if we subtract 1, so in this case 1 minus this, then it should give me some lower bounded interval. And then if we add it, then it should give me an upper bounded interval. Okay, so a word of caution, we rarely can tell exactly how big the tangent line error is. That is the exact difference between the function and its first Taylor polynomial. But the point of having this error bound is to give some control or bound on how big the error can be. And sometimes we cannot tell exactly how big f double prime of the absolute value of that is, but many times we can say it is no more than some number of m. And that's what's important, right? We want to be able to bound our error. Smaller numbers m, of course, give better or smaller bounds for the error. In example 1.2, right, we found the maximum of the second derivative on the larger interval I. And there is actually a better or smaller bound on the smaller interval j, but that bound would have been hard to find before we even knew what j is. Right, so I guess just to summarize what we did, well, really, it's important to not, sometimes it's not really all about finding the exact solution. It's more about finding a solution and checking, is this a good solution? What I mean by good is that, can we say that it's a good enough solution that it minimizes error, right? Because not everything in the world is exact. So there is some error, there is some room for improvement, and from there we have to kind of build up on that. Okay, now I'm getting a bit weird. Okay, so that's it for this video. I find this topic really interesting, personally, in my opinion. But yeah, I hope you guys enjoyed, and I'll see you all in the next one.